Well, welcome to the meeting for August, everybody. Tim. So we're going to start the meeting 4 minutes late. We have a few commercial announcements and a very slim bit of business to cover. And I've been focusing on the talk, so I don't remember what we were going to do before that. So I guess
just check out the slides. Yeah.
Oh, good.
Thank you, Chuck McPartland, for the great planetarium show.
Yeah. Okay. So I guess we're going to go to directly to. Well, this did force me to dig up a picture of myself. It's back there. My 12.5 inch in my backyard.
Yay, he's got an 18.
My first project after I retired in 2006. It's fantastic images. It's the only mirror I didn't make. It was made by a guy, his name escapes me right now, but he started doing lightweight mirrors called conical mirrors. And Royce, that's it, yeah. And so I bought a mirror from him, and that is a fantastic mirror. So I guess we'll start with Chuck doing outreach.
No, it's okay.
Oh, we're going to do the merch.
All right.
What's in the treasury?
I promise the talk will go smoother.
The merch show.
Thank you, Jerry. My name is Pat McPartland, as you see on the...
Oh, sorry.
You make me blush. So good evening, everyone. I sell the clothing and the tote bags and the caps and the mugs, and we're getting out of the clothing business, and I just have some small and some extra large and different styles. You can see me afterwards because I still have them all tonight. And the tote bags are fantastic. They're, you'll see some that we carry around. And what else? Oh, on behalf of the secretary, there are name tags over here. So please, if you're a member, your name tag should be in there. If it isn't, go after the secretary. He's back there in the second last row.
Wait a minute, you're still making it.
So that's it for me. Oh, and back to you.
Thank you, Pat. And now, Chuck.
Jerry? Okay, outreach has quieted down a little bit. We're in our summer campgrounds frenzy. So next thing coming up, of course, is tomorrow night, second Saturday of the month, weather permitting, is right here with the Public Star Party. And 8:30 to 10, but set up at 7:30 if you want to take some time to get all set up in line. If you're one of the dog snobs or the sea star snobs, you can just come 5 minutes before. And then on Wednesday the 12th, it's not only the peak of the Perseid meteor shower that evening, but the Carpinteria State Beach outreach.
Yes, that's it.
And yeah, and then on the 14th, it's Refugio State Beach, Friday the 14th.
Ooh.
And then the following Saturday, the 15th, it's Kachuma Lake. And then the 18th, Tuesday, is third Tuesday of the month this year, is Telescope Tuesday at Commuter Rail Marketplace. There's a lot of light there, but we look at the moon a lot, and the sea star snobs can pick up deep sky. And then on the Friday, third Friday of the month, is our regular public telescope night at Westmont. And then we don't have a Kachuma. That's one Saturday that we set up with them, and then somehow it got dropped. So
Why is Refugio twice?
because we're going there twice. Okay, so on the 28th,
Right.
Friday the 28th, we're going again to Refugio. That's a really nice spot. It's dark. And you're looking out over the ocean, and there's laminar airflow down the canyon usually, and good seeing. So and plus you can just park your car and just dump your scope right next to it, so it's easy.
Really nice.
Yeah.
Very nice.
And then Kachuma again on the 29th. So that's our August. And then early in September, we're going back to Refugio, but on a Saturday on the 5th, on the night after our meeting then, which is on the 4th. So that's outreach. And there's propaganda over here by the door, star maps, moon maps, and bookmarks, and if you like paper, we got paper. Thanks.
So we're having a meeting here. And then we're going to Refugio in September? So
No,
you said-
the next night is Refugio.
Oh, okay.
Yeah. Okay.
Okay. Diane, do you have anything you want to say?
Sure.
Diane is our events coordinator.
Hi, everybody. Our next event is going to be the camp out at Kachuma Lake, and it's going to be really fun, October 16th through the 18th. And there is a talk on that Friday at Santa Barbara City College, so we'll need to just work out the logistics for that Friday with Chuck. But you can please come up for the potluck, which is on the 17th. And the club actually provides like tri-tip, chicken, beans, bread. And then all you need to do is bring like a dessert or a side or appetizer. And the potluck is gonna start at 4 o'clock. But if you come early, we'll have some appetizers and hang out, and it's gonna be really fun. So mark your calendars, and we hope you can all attend. Thank you.
Thank you, Diane. And now I'll introduce, I think that's all we have of the business.
Just real quick, there is
Oh, yes,
just
sorry.
equipment available if you want a telescope for quite a reasonable price and some other accessories, let me know. I'm the equipment coordinator, you can see on the website, but try to get hold of Tom about the equipment. All right, and next, it's our list of people that are volunteers. And then we got someone named Ronnie Heron, something.
Who's going to introduce the speaker?
And also kind of showing up there is, there's solar viewing here at the museum that a bunch of AU people help out with in the observatory
It's on Sundays, right?
on Sundays.
Want to stay up here with me?
I guess.
Good evening, everybody. You got a real treat in store, I think, because I work with this man every week. So does Tim Crawford, who never comes to these meetings.
Here tonight.
Definitely going to kiss the boss's ass tonight, aren't we?
Yeah.
And I will not be giving Jerry a cup or a tote bag. He already has 97 of them at home.
Oh, no, he needs more.
Check. We're going to write you a check. We do get our hats at the same place. And for those of you who don't know about Monday mornings, this man could be a Boyda Hall physics professor. In fact, we're just calling Jerry Wilson, but he's had a PhD all along. He's Dr. Wilson. Tonight we're going to call him that. In any event, I want to do my little, what I call entrance poll. They do exit polls, you know, in elections, so I want to find out who our guests are. Anybody new, first timer? Okay. We have one gentleman though that I met with, where is he? He's right there with the cap. Who was one of our first hand up, that was you, right sir? You joined a month ago?
No, about a year ago.
Oh, well, I just asked you, how long have you been in the club? And you said a few months. Okay, but at one time we get you. Who's been here before but not a member yet? Anybody? We're not gonna let you get off the property, man. And here's my friend Mike Hardwick, the star of the threesome we had 2 Decembers ago, talking about his, what, 5 or 6 scopes you own?
Yeah, astrophotography stuff.
Let me just run down before I introduce Jerry, who's coming to town. We got a booked up solid coming attractions next month, first Friday. Another one of those rising young stars of science that we try to give a helping hand to and offer them a shot, and we're pretty lucky. These guys turn out to be good. And that would be Dariush Imani, a UCSB grad student heading for his doctorate in particle physics. Promised to entangle us gently in the mini, micro, nano world of quantum mechanics. I ask you to be gentle, especially with the formula and the equations. But it should be a good program. That's the 4th of September, 1 month away. 2 for in October, very rare, 2 for 2 speakers, 2 different dates, a couple of weeks apart. October 2nd, the return of speaking of former grad students. She was at UCLA, heading for her doctorate years ago before the pandemic, and we had her in here twice. She's now at our university out here with a postdoctorate fellow, and her name is Briley Lewis. And she's just great. She's very sweet and very, what's the word I'm looking for, feisty. She loves talking to us. The middle of the month, October 16th, we're not sure. You better get there early just in case. It's open to the public, 145 seats inside BC Forum down on West Campus, City College, where Dr. Alexei Filipenko, who's in charge of UC Berkeley's astronomy department, and as a veteran of this place right here, one of the original members when we were known as Santa Barbara Astronomy Club, SBAC, he will return. He insisted, he was the one that called us. I don't suppose Sean Kelly is here. Okay, he's got summertime blues going for him. Friday, November 6th. What?
He's in Spain.
Well, that's a cheap excuse. He can still take a hop a flight. I think Trump has another plane available. That's gone somewhere.
Solar eclipse.
Dr. Howard Wee, very nice gentleman who came into town with Dr. Korngut November of last year. He's going to talk almost a year to the day after Dr. Philip Korngut talked about the Sphere X. That was November 7th, last fall. And his fellow Caltech colleague, Dr. Wee, came along, liked us, wants to talk to us, originally booked for this evening, but something came up. I think he had to run a seminar or a big conference or something, so I moved him to November 6th to talk about a microwave telescope called the BICEP that NASA runs down on the South Pole. And I'm anxious to see what the sky stuff he's going to show us looks like. Stars we don't normally see. So that's November 6th, the Friday. December 4th, our club's yearly in-house We Can Do It members only talks. We got 2 of them, local guys that are going to do a great show. One of them is Tim Crawford. Questions I'm normally asked. I think you get 3 of them right at star parties.
Yep.
And then we ask our outreach guy in charge, Chuck McPartland, on a great occultation he pulled off and a discovery. I'll just leave that in case you haven't heard about it. He will be the second one on December the 4th. Our president has quite a history, qualified to be a great science speaker for the club. Once a week for over 5.5 years now, he has become our Monday morning professor of astrophysics at the club's YouTube blog podcast called the SBAU Astro Hour. Gotta tell you folks, we cover everything in the cosmos. Jerry's as good as any of those high-priced professors out at Habitable. Recently I came up short for a speaker when the August guest had to postpone, as I told you already, and so Dr. Howard will be here in November. Jerry is here now. We should have him probably once a year. PhD in physics from UCLA, condensed matter physics. You'll be right at home next month with that kid from particle physics.
No, not even close.
Not good close. I mean, we're talking Raytheon, some of our research, Hughes, all kinds of space projects out on West Hollister. Retired in 2006, worked as a consultant at CYAN, C-Y-A-N? CYAN Systems till 2018. Ladies and gentlemen, our professor for tonight, our speaker, Dr. Jerry Wilson, the president.
Thank you, Ron. Well, this talk is going to turned out to be a very interesting one. I started looking at it, I found something online and started following the trail about it, and it's kind of blended my professional history of working at Santa Barbara Remote Sensing. That's okay, doesn't bother me. So, in building instruments for spacecraft, and then, as you'll see, this is the next generation of a spacecraft. But anyway, this is a search for habitable worlds. And as you've noticed, we've been looking around and seeing exoplanets and trying to measure them, and we get a lot of false alarms. We're obviously looking for life and we're hoping to find it. As you'll see some pictures in here, we found worm-like structures on rocks that are reported to have come from Mars, and but that wasn't convincing. Then we found, we took some Martian soil, we put it in some broth on Mars, and got what we expected for metabolism, and that wasn't convincing enough. So, and I'm not trying to say that it should have been. I mean, it's really a genuine mystery. And we've had a couple of things on Mars that have found suggestions that it's there. We've also looked at exoplanets, and that's going to be the focus here. And we have looked at the atmospheres of those planets with the James Webb and the precursor, the Spitzer. And we have seen chemicals that are only produced by life, until someone who didn't believe that pointed out that they can be produced by inorganic chemistry too. So we keep building a little pile of non-firm evidence. So they have decided, NASA has decided to build a satellite that's going to go out near the moon at the L2 point, called the Habitable Worlds Observatory, or WHO, which I call WHO for short. And it's part of NASA's Great Observatory program. These are the flagship things for NASA. They're the most expensive. And this was the first one put up. This is obviously the Hubble Space Telescope. And you can see it being lifted out of the cargo bay of the space shuttle. And that's been up there for decades. It's received visits from it. It's unusually high for something that we can visit. But they did have a shuttle mission up there to go up and install and update some equipment. And it's been going on. I think they're planning or hoping to plan, if the budget doesn't get cut and cut again, to go and refurbish it with newer equipment. And
That's good.
What they're proposing now, and I'm going to talk about, is also something that's going to be planned on being visited in the event it needs repairs. And but this one's going to be out at the L2 point. So that's going to be a pretty ambitious trip. Okay. The next one was launched in the 90s and retired in 2000, was the Compton Gamma Ray Observatory, specialized in observing very high energy gamma rays. Then we have the Chandra X-ray Observatory, continues to provide unprecedented X-ray imaging of extreme objects like black holes and supernovas. If you want to make a telescope to look at X-rays, that is a real big challenge, because anything you put up there like a lens or a mirror, the X-ray is going to go right through it, so you don't get an image back. So there's an elaborate process that places like Santa Barbara Research Center went through, where you make a series of cylinders nested inside each other, and each one is slightly curved to make a signal parabola that comes back to a focus back there. And the X-rays only skid along the surface of these materials, so it gives them the thickness so that you actually get the X-rays to not pass through your instrument, but to focus on a detector. But that's another talk. This is the Spitzer Base Telescope, which is an ambitious infrared telescope. It was retired in 2020, and James Webb loves to take pictures, old Spitzer Space Telescope pictures, and show how much better James Webb does. This one does not go out as far in the infrared as James Webb does, but it showed a lot of interesting stuff. It's a very, quite a bit of papers were published. Then, of course, most recently, the James Webb Space Telescope. We have a member of the club here, Peter Love, who was a detector specialist on that thing, and he gave a talk on that. It was at the same place where I worked, along with Peter. And we worked on it in the 90s with a launch date estimated to be no later than, say, 1999. And, but they kept having problems when they ran it through practice sessions, especially with unfolding all these heat shields down there. So that one is what took so long to get that sorted out. Now this one is going to be launched on August 30 this year. This is the Nancy Grace Roman Space Telescope. And this observatory is a very wide field view, similar wide field version of Hubble. So Hubble's very narrow field focuses down on things. This one is going to do big surveys and look for things that move. So it's going to cover that in a few nights. I think it's going to cover the entire sky and then keep doing it again and again. The amount of data that it's going to handle is going to require its own, what do they call that, data center. So that is going to, that's something I'm looking forward to watching that turn on. And then we have tonight's talk. We have the Habitable Worlds Observatory, which is NASA's next designed flagship astronomy mission. It's slated for launch in the 2040s, probably closer to 2060 in my estimation. In physics, when we get a date that something is targeted for, we always apply the pi rule, which means we multiply the time by pi. And that is much closer to what actually happens, but they will never admit it. What it's doing is, the primary thing it's doing is it's looking for biosignatures. It's looking for uncontrovertible observatories of life. So it has a list of things that are at least 25 Earth-like planets. We don't know exactly where they are, they haven't been discovered yet, and analyze their atmospheres for oxygen, methane, and other gases that indicate life. Beyond that, there'll be a lot of other things that it will look at about planetary evolution. So this is a representation of part of the 6,000 exoplanets we have discovered so far. And
Jerry, do you need a laser pointer?
yeah, I
now?
was just thinking of that.
Let's see, I got a bright one and a dimmer one. Let's see.
Green and purple.
So this is
You have a purple one?
the other one too. That's a dim one, but it might be stronger. This one's a real bright one. No, those are the bright. No.
Thank you. chart. This is planet mass.
Microphone.
This is planet mass, and this is in Jupiter masses. So one up here, this is Jupiter mass. So everything in a straight line across here is a Jupiter mass. This is 10 times Jupiter mass. Jupiter's already a giant. These would be really ridiculous. And this one is their orbital period around their primary stars. So this ends in days. So these orbit their star in one day. And so they are really close, and they're hot. So we are here at, 365 days, so there's 100 days, 1, 2, 3, so Earth would be right there, and there it is. The planets of our solar system are on this chart, and they're indicated by these red circles there with a dot in them. This is Mercury, Mars, Venus, Earth, Uranus, Neptune, Saturn, and Pluto, right there on the one line.
Jupiter.
What did I say?
Pluto.
Oh, sorry.
Same thing.
Yeah. I've always wanted to meet Neil deGrasse Tyson and say, I'm not over it. So anyway, the thing that we're looking for, because of the analysis we're going to talk about, we really are looking for things that are in this region here, not Mercury, but Mars and Venus and Earth primarily. For reasons you'll see later, we're not interested in these planets because we're looking for not only for life, but life as we know it. And these planets do not have a surface. So, and they do not have transparent atmospheres. Interesting chemistry, but nothing else. They may have life, but we're not going to be able to communicate with it easily. And I've also thought about the fact that if the planets like this do develop life, they're never going to develop a rocket to take off from it. It's too strong gravity. So what we're really looking for is planets in here, and you see that this area here is empty. So this is the area that this new satellite is supposed to find candidates in. Well, I guess I'll do this slide. Let's see.
Go to the far left and click on 10.
Yeah, I tried that.
Oh.
Do you want to be in slideshow mode? Go up to slideshow at the top and
Well,
maybe.
I got out of it.
There.
Okay.
Go up to slideshow at the top menu.
No, it's right here at the bottom.
Oh,
I'm doing
Oh,
everything right.
all the way down there.
See, the slide that was right there. Oh, yeah, you gotta move with that, yeah. Okay, so which one do we get right there? This one? No, just right, like one more. There. I don't know if one turns out, we're gonna go with it. So anyway, this one, this is the observational hurdles that we have to face to find those planets that are in that forbidden region. Earth-size, potentially rocky.
Microphone.
Darn. It's weightlifting.
Most of the Earth-sized, potentially rocky planets discovered so far have been detected with indirect methods, transit, radial velocity, and very few have been imaged directly. The new telescope is going to image them directly, but it's not going to image them so you can see surface features. That is simply impossible. There's no telescope we can build from Earth here that you can even see the features on Proxima Centauri, for example. It's just too far away. So what they mean by direct imaging, is that you can see the star, and then next to it you can see the planet, the exoplanet. And what we want really is not an image of the exoplanet, we want a spectrograph, a spectrogram. So we want to catch a planet's transmission or emission spectrum. In order to do that, stellar light must pass through the thin ring of the planet's atmosphere during a transit or when the planet is directly imaged. The issue is obviously that our Earth-sized planets around a G-type star are incredibly small and dim compared to the host. So we have to block out that light. Let's see, current technology, yeah.
Oops.
No, of course I did something on the trip.
Well, we're still seeing your screen. So.
I know, but I can't advance the slide. I advanced too much.
Get back to slideshow.
Yep.
Get them else in. That must be that fourth one.
Okay. Okay. Now, this one we went over. This is the graphic version of what I just said. These are a graphic version of what I said. These are spectra taken with either the Spitzer or the James Webb Space Telescope. And this shows the parent star and then the exoplanet going around it. And we want to get a look at the surface of the planet here, or not at that planet, but the atmosphere here, and the transmission of the planet in this little green ring. So this is very challenging because this star is going to be very bright, a billion times brighter than the planet will be. We do have some spectra of these types of things. They're mostly of giant planets. But here we believe that we see H2O and methane, CO2. And here we see a bunch of CO2, CH4, CO2, if they say so. But it's not a really good spectrum at all. It's got to be better than this.
Is that thing rotatable?
I don't know. Now, another factor in this is that University of California at Riverside developed a model for this project called STEHM, which is smaller than Earth habitability model. And what they did was they wanted to know, does the planet's size play any significant role in the atmosphere? And it certainly does. We're 4.5 billion years into the Earth's life, and we've had an atmosphere the whole time. So this model looked at atmospheric concentrations in bars. So a bar is one bar is one atmospheric pressure. So that's, well, that doesn't make sense.
It's CO2.
But yeah, it's carbon
Yeah.
dioxide. Yeah.
Yeah, no, I'm just trying to figure out if it's a trick to remembering what the pressure is. But anyway, this is, they looked at different Earths. This is the radius of the planet, one Earth, and down here is half an Earth radius. And these, so there's 6 here, 1, 2, 3, 4, 5, 6. So once you get down below 8/10 of an Earth, say here's Earth, here's 0.9 Earth, here's 0.8 Earth, down below that, they cannot retain an atmosphere. They, and this is assuming a pure CO2 atmosphere. So these at this concentrate or this mass, they retain an atmosphere essentially indefinitely over 10 giga-years or 10 billion years. So the planet Mars cannot be a candidate for this. We're not going to look for exoplanet Mars. We need to have them somewhere between 1 and 0.8. We can have them a little above. I must be feeding back somewhere. But it needs to be above about 0.8 point there. The thing they model is they model what they call a stagnant lid planet, which means there's no plate tectonics on it. Among the planets that we know, Venus, Earth, and Mars, Earth is the only one that we know for sure has plate tectonics. So they're taking that as if that means that we have to have, for life, we have to have the geochemical reintroducing the atmosphere and recycling the atmosphere as the Earth does. So we're really narrowing down different factors in the Drake equation so that they're getting very, very small. The fact that the Earth has plate tectonics is believed to be directly due to the fact that we were hit by Theia, another planet that was a protoplanet that was about the size of Mars, and it stripped the surface off the Earth, and it threw the surface up to become the moon. So the moon is basically made out of surface and a little mantle of the Earth. It's very light, it doesn't have a significant core, but its chemistry is identical to the chemistry of the Earth. So that's an unusual thing, and we have, among the moons that we know about, we have a very big moon for the size of our planet. So these things might be necessary conditions for habitable worlds. So, yeah. Now this is an early hopeful in the TRAPPIST-1 system. It was the top one shows the initial discovery idea of it, and then once James Webb went online, we see that the lower version of it is more accurate. That shows all the planets there are. Few of them are in the habitable zone, but this is a red dwarf star. Just like 75 to 80% of all stars in the skies are red dwarfs. So we're probably going to find a lot of planets around a red dwarf. All these planets are interior to the orbit of Mercury around our sun. But it's technically possible for D, E, F, and G to be to have liquid water on it. The issue is that a small star like that is going to have small planets. So the small planets are too small to retain an atmosphere, as we saw by the previous one. And a small red star like this is prone, they're very active. They're prone to flares and solar winds that would strip the atmosphere from those planets. And we have got recent looks at planet, I think D it is, and it's definitely not got an atmosphere. So these are most of the planets we're going to find. This is a hot gas giant that we thought was a water planet. And it shows here a strong carbon dioxide band up here. Carbon dioxide seems to be the common denominator, at least in early atmospheres. We've had a lot of things that have interfered with ours, which we'll get to. But this one is not a candidate for us looking at it for this reason, because there's no surface there to form life on. This is the same one, K218b, but this is with a JWST transmission spectrum. And this is the one that made the news once a couple years ago because they said dimethyl sulfate, DMS, dimethyl disubstrate, and I can't read that one over there, but it's a similar chemical. And they said that can only be produced by life. This is primarily a water world that's loaded with water, but there's a lot of ways you can get those dimethyl sulfur compounds without life. So we need better evidence, and you see the spectrum that they have. It's not a terribly, it's not what would be considered a high resolution spectra. This is the water and CO2 component of that same planet, planet. And it orbits, I think on the previous slide, it said it orbits around its sun every 33 days. So it's way too close. It's very hot. Oops. A little too much pressure. Oh, yes, okay. Good. Okay. And this is, as I mentioned earlier, that microphotograph of that rock from Mars, getting our hopes up again. But they do look like bugs. But there's no other evidence to suggest that there are life, or even prehistoric life. So this is the atmosphere of our solar system. Mercury doesn't have one. The big ones that we're interested in are Venus, Earth, and Mars. And you can see the Earth has nitrogen, oxygen, argon, and a trace element less than 1% of CO2. The Mars and Venus are massive CO2. But they don't have plate tectonics, and they haven't developed life, which takes away a lot of the CO2. So in Earth, we're going to show a picture of this so you don't have to read every word here. But the key thing is the second indent here, oxygen methane disequilibrium. It's a simultaneous detection of highly reactive gases like oxygen or ozone alongside methane, because these gases react and destroy each other, so they cannot coexist in stability in an atmosphere. So what does that mean? It means there's something down there making both of them. So, as a matter of fact, it lasts in the atmosphere less than a year. So that is the single biosignature. It's the primary biosignature that they're building the telescope and the system to be able to pick out that. Now, they also mentioned down here a vegetation red edge, which is going to be, for the atmosphere is clear. Let's see. Yeah, this is a graph of the Earth's atmosphere. Spectrum is taken from 3/300ths of an astronomical unit away. So how many miles is 3/300ths of an astronomical unit? Anyone pick?
1/10 is 15 million, so 2/100 is 1.5 million times 3, 4.5 million.
That's about right, yeah. It's taken from a spacecraft as it's going on its mission somewhere else, and it looks at the Earth spectrum. This is a high-resolution spectrum, and they want to get this resolution because they want to be able to resolve these O2 lines from the O3. They want to resolve the water and the methane. And this is out to 2.5 microns, and this is 1 micron, which is where silicon cuts off. So this is all near IR. This is the visible from about it's in here about 0.3 to 0.6 where hydrogen alpha is. So this is near UV. Actually, they call this on this report a far UV, and this is near UV. So this is their target. They want a spectrograph on a telescope that is capable of catching this amount of faint light and resolving features like this.
You're getting good at that, Gary.
What's that?
You're getting good at that.
We're breathing in every bit of that, right?
Now this is a Landsat image, not a terribly high resolution, but Landsat wasn't a high resolution imager. I think Diane said she worked on Landsat. And this is what's called the red edge in the fields where, photosynthesis is going on. Now this is one of the first imagers when it was developed and put up by Hughes, and just largely to survey the Earth and see what you could see. And it turns out these became very, very important. It's a low resolution early technology, but it became so important that Congress said you have to have what they call the Landsat continuity missions, which means that you have to put up a fresh satellite every 10 years that has exactly the same technology as the 1960 version, which nobody wants to do. Actually, aerospace companies actually compete to not win the Landsat continuity mission because there's just no money in it for us. But back when this was taken, and I started out, you could pick a place on the Earth, and they would go send the Landsat satellite over, and they'd take a picture for you for $50,000 per click of the shutter. And it turns out this was wildly successful because any guesses who wants these? Financial institutions. They want to see how the crops are doing each year, so they know what kind of futures to buy. And the color of the spectrum, and that gives you the health of that particular thing. Corn, wheat, oranges, anything. So that's what the government keeps that going for that demanding customer. But anyway, the Earth, as it is today, is represented in the top one. Oxygen, ozone, nitrogen, water vapor, carbon dioxide, methane. But as it once was, nitrogen, water vapor, carbon dioxide, methane. So we're also looking for Earths that were the way our Earth was once before, so we can understand the evolution of what's going on. So the Earth history timeline goes real quickly from when it was first molten to it differentiated, meaning the heavy stuff went to the core. We developed a magnetic field. Mars and Venus do not have magnetic fields. They do not have a dynamo inside. And that is key for life on the planet. The oceans formed, and then down at the bottom here you see 3.5 billion years ago, first microbial life. They deposited oxygen into the atmosphere. That killed off the cyanobacteria. And then we had a period called the snowball Earth. From 720 to 635 million years ago, the Earth was, for some reason it's not completely understood, but is believed to be a sudden drop in the Earth's CO2. And also our plate tectonics formed one large, wasn't Pangea, but an earlier one before that shut down volcanic activity, so a lot of greenhouse gases were not going into the atmosphere. But eventually volcanism caught up with it, it dumped CO2 back into the atmosphere, and we got back to the scenario we love. So then we got complex life, and there we are. So we're actually interested in for the science of the things, finding an Earth as it was. So the architecture and engineering of NASA's SBAU are currently being matured by the Technology Maturation Project Office, and they're making a series of EACs, that is exploratory analytical models, and they are doing very thorough analysis of those, each model. So a single contract has not been decided on yet for this satellite, but NASA has awarded early stage 3-year technology development programs, and these are going on. Study contracts to 7 different companies, including Astroscale US, L3 Harris Technologies, Lockheed Martin, Northrop Grumman, to mature critical optical surfaces and architectures ahead of a planned launch in the 2040s. So these are three of the, looking down the throat of the first three EACs. There are a total of 5 of them that have been done and analyzed in great detail. Number 5 is so far the champion. And you can see down here that at the very bottom, servicing mandate, NASA officially pivoted the mission architecture to require robotic in-space servicing and maintenance. That is, it's going to have to go up there on Starship. So, these are pictures of each of the EACs that's been analyzed. And if you know a journal or a series of conferences called SPIE, S-P-I-E, Society of Professional Industrial Engineering, they have disclosures or published papers to these teams that are 100 pages long each, and they thoroughly analyze the optics, the thermodynamics, everything. Now this one, these are going to have to be, let's see, did it say in there? No, these are going to have to be cooled optics, not as cold as the James Webb is, but they're going to use Stirling refrigerators on the thing, which are little piston-like things. And there are several of them, and they're going to keep it cold, so the infrared detectors are happy. They don't produce a lot of dark current. And those things vibrate. And the thing that is critical about this telescope is it can't vibrate. It's got to be insulated, the detector. They want a really steady picture. So, some really quick relevant facts. EAC 4 and EAC 5. You see up here at the top, launch vehicles. Next generation Blue Origin, unfortunately his just blew up. And this is the Space Launch System, which is NASA. And I noticed that the Starship is missing from the 4 and 5, but it was up here in an earlier study. So, number of mirrors. The mirror size here, primary mirror is 6 meters, 6 meters and 8 meters under EA3. And down below, it's 6.5 to 7 meters and 8 to 8.5 meters. So it looks like people are claiming that EAC5 is going to be the design, most likely. But it comes out in the details of the numbers.
That's heavy.
What's that?
That's heavy.
Yeah. So if you, and some of the things you showed earlier, I showed earlier, there were segmented mirrors, and then there were large chunks of mirrors and stuff. So, this is the detail. Okay. Well, that is the talk.
I'm sure we're ready for Q&A.
Yeah, I'm looking forward to sitting down on my TV and watching the thing go up.
Yeah.
How are you gonna tell when these exoplanets, whether there's volcanism or, you know, frozen solid, yeah, I mean, how are you gonna figure that out?
Not directly, because we can't image things on a solar
Yeah.
on the planet, but we can tell by the gases they pump out. Most CO2 seems to come from volcanoes. And a lot of water too. Jim?
Jerry, you told me this once before, we talked about the volcanism, the dynamos, but does the core have to be molten to do that, or?
Somewhere it has to get liquid, it has to get magma. It doesn't have to get it from as deep as the core. Just tectonic plates running against each other produces the molten rock. You know what do they call it, the Ring of Fire here on the Pacific coast of
Yeah.
Japan and stuff? That doesn't go very deep. It's just the friction of all this mass.
And that creates a magnetism? Is that?
No, that creates molten rock for volcanoes.
Okay.
If you meant magnetism, that comes from the core. Yeah, that comes from the core, and the core has to have some kind of dynamo effect. That is, it has to be a rotating set of dynamos that vector add to the current, the magnetic field you get, or a big dynamo. And small planets cool off very fast, and that's what happened. That's why Mars doesn't have
That's what
a
happened.
dynamo, because its core has slowed down and stopped.
And they can't retain, those planets can't retain an atmosphere.
Those planets are unlikely to because they're bombarded by energetic solar wind,
Okay,
and so that takes it away.
okay.
Well, you probably covered this, Jerry, and I missed it, and I apologize if you did. How do they know which exoplanets are in the Goldilocks? Just because of all these gases? That indicates they're in the perfect place?
No, they have to be able to see the star and see the exoplanet, and they know the distance between, and so they can figure out the temperature range that that planet is going to experience. And then that will tell them whether it can have liquid water on it or not. And that's the sole definition of the Goldilocks range.
Spectrographs don't give you temperature, do they? It wouldn't tell you it's average 78 degrees on this planet. It doesn't know. It's all just different compounds and elements.
You can tell, if you can get a look at the blackbody curve of the thing, you can tell where it peaks, and you can determine the temperature very well. But we're looking at lines, molecular lines here. So we can tell the temperature of the star, but not of the planet.
Well, they're starting to say that any life in this solar system of ours is going to be on gas giant moons, perhaps, or outside the Goldilocks zone. I think that Mars is outside, isn't it? Maybe at one time it was in.
No, Mars is in the Goldilocks zone.
Is it? Colder than
If it
it?
had an atmosphere, there could be lakes on Mars that are liquid water.
Okay.
The reason there aren't is because there's no atmosphere to hold it in. The pressure's too low. It lost all its atmosphere a long time ago.
One thing we're never going to be able to see are these frozen moons around exoplanets that might have deep oceans and thermal vents and.
No, I think there are, we definitely know there are moons around Saturn and Jupiter that have,
Well, yeah, that's in our solar system.
Yeah.
I'm talking about they'll never be able to find them around other stars.
I don't know, I wouldn't say never.
So, I tell you what's gonna happen, they're gonna find that there is life on this planet. We know it, and it's gonna drive us nuts, because we'll never be able to go there. Find out, land a rocket and see.
How did you find
Well,
Yeah, this is,
it's a good question.
we're looking for life as we know it, with RNA and DNA and stuff. Yes?
You mentioned how key the moon has been in the Earth's geologic evolution. And that the size of the Earth, being able to keep a molten core and
Right.
electromagnetic field on. Is there, the future search, are they going to be trying to find planets our size with a moon? Or is it
They're
less?
gonna try and find planets our size,
Just our size?
and if they have a moon, they're not gonna ignore it.
But having a moon is not a primary,
I personally think it is,
I kinda do
but-
too.
but we don't really know that yet,
Yeah.
so.
How would they,
So, but
how would
those
they,
parameters that they're looking for is the size of the Earth, is the size of the planet, basically, and the distance from the sun?
That's one of the constraints they're looking for.
Because the big, is,
But
Is
they
there
want
a
the
paramount
diameter, the
constraint?
diameter of the planet, because it has stuck atmosphere. Oh, and also, around those red dwarf things with, for example, the TRAPPIST system, when something's orbiting that close and that small, they eventually lock up, so they always face the same side to that star. That's not a condition for life. So,
oh, I did have another question. You said, what, 75 or 80% of the stars are these red dwarfs?
yeah.
So are we gonna quit looking at the red dwarfs because of those limitations? I mean, I'm just asking what the
No, we don't
parameters
look
are.
for the red dwarfs because they're so dang hard to see,
Yeah.
so they're very faint.
I guess what I'm asking is, since there are so many red dwarfs,
Yeah.
and they pose problems with these near planets locking, et cetera, is these projects going to be looking for the other stuff, not the red dwarfs, but the
Well,
other
we're not
stars
trying to
like
find the
ours?
red dwarfs. We sort of ruled out, from the parameters, ruled out those as a habitable planet around it. But they're probably gonna collect data on a lot of these things. The primary mission will only be satisfied when they've found 25 of the life-like, or Earth-like planets that could support life. But I'm sure that they'll hope for all sorts of surveys of these things.
But what about, the Earth has a magnetic field which undoubtedly
Yeah.
can be detected, and it may or may not have an effect on life. So are they gonna look for magnetic fields around these planets?
The magnetic field is hard to spot.
We should be able to detect something.
Yeah, well, you can't see it around the moon or Mars, because it's just so faint. Actually, they each had one at one time in the past, and just like the C4 spreading, when new lava comes up in the middle of the Atlantic Ocean and it spreads apart, it goes from molten to cool, and it orients with the local magnetic field on Earth at that time. So you can go back and check the rock and see what the magnetic field was, where it was pointing and how strong, by moving away from the spreading center of the ocean. Now, on the moon and Mars, there are regions of the moon that have a magnetic field, but they're local regions. But when the moon had a magnetic field, that was molten, and then it froze. And so there's a few places on that that are called anomalies, but they don't represent anything that's moon-wide. They're just local intrusions. Yes, Tim?
Last one for me is, it seems to me that Earth history timeline that you talked about, it seems that's super important. To be able to compare what we're looking at to, are they gonna be able to see something that would give us an idea?
Well, I'm just gonna guess yes.
Maybe, I mean, I mean, it would be really nice to be able to pick something after the snowball Earth.
You gotta realize that we're sitting here with a technology, a modern technology about 200 years old,
Yeah.
and human life on the Earth about 1 million years. If you count all of our ancestors that were swimming in trees and stuff. But that's a narrow slice out of things. The fact that we're gonna see something out there that's exactly at the same evolutionary stage as us is just astronomically against it.
Okay.
So we could say, oh, this looks like the Earth with its atmosphere, say, in the Jurassic period.
Okay.
Something like that. Or when there's microbial life only.
That makes sense, that makes sense.
Jerry, do you happen to know all the elements in the famous equation of late astrophysicist Frank Drake? How many items were in a row there?
I think there were 7.
7 that he claimed we need. Gotta have every one of them. One of them was a moon, wasn't it?
I don't recall.
Does anybody know what they're in the?
But some of these, after I prepared this talk, I realized that some of the factors in his equation are minuscule. It's not like, 1 or 2%, it's way down there. How many planets do you think in a neighboring solar system have a planet that has no crust on it because it got hit by another planet and it now has that as a moon? Odds against that are very, very good.
Unless they find more life in the solar system somewhere else that didn't have that instance.
Now, we have tried to look for exoplanets that have our technology on them. One of them I know they were trying to do, but I haven't heard any results of it, is they're trying to look at the dark side of exoplanets to see if anyone left the city lights on. Because that would be definitely something that doesn't happen naturally.
So those videos,
Tessa?
When you say life as we know it, are you talking life as we know it going back from the point that we had little prokaryotes?
Anywhere along this chain
Fair enough.
is life as we know it.
Okay, good, thank you.
Okay.
there could be silicone life, could you?
No,
There can be silicone
there's
life?
not enough organic-like chemistry in silicon to support the life that we have in carbon.
There goes the unpromised strain.
And there was a porta.
Tom?
Jerry, has anyone ever looked at Venus and thinking that they could put some sort of a, an algae, something, photosynthesis, using the carbon dioxide and convert that to oxygen? Is that,
There are teams all over the place that are planning how hypothetically to terraform Venus and Mars.
Wow.
Get them to be like one, and it's not looking good.
Yeah.
Sulfuric acid.
Total recalls.
Especially on short time frames.
Kind of hard to get by the acid rain.
Elon Musk has this idea that the whole problem will be solved if we use our entire nuclear arsenal on the polar ice cap of Mars, because that will evaporate into the water, and then it will rain all over the place,
No.
and the atmosphere all done.
And then be gone again.
Yeah, that scares me.
The radioactivity will throw everything there, unless you, not to mention what it does in space. Nuclear explosion.
Well, thank you all.
Let me say one thing before you stop. If the president were up to it, would you be objectionable to a yearly speech by President Jerry Wilson?
gotta ask Jerry.
I gotta tell you, I'm having nothing but trouble this summer. I've sent out 100 emails, and I've gotten back one reply, and that was Riley Lewis, September. Because the whole world has gone to AI and spam filters.
No.
And I did have some success, ladies and gentlemen, with writing a good old-fashioned snail mail letter on notebook paper and folded it up and had my scrawls on the envelope. And it shows up in their mailbox, and it's not one of these AARP solicitations that you can throw it away. This is somebody writing them. That's how I got our May speaker.
It's just being bitter.
No, I'm hoping you guys, I know Tessa sends me names all the time on email addresses, but they're East Coast people, and I'm not sure how a video or a Zoom, a talking head would go. I'm trying to get live people if that's possible.
Yes,
That means from here.
no dead people.
All right, we'll talk about it, everybody, I guess.
This meeting is adjourned.